Hello again. Welcome to Physics 371 Online. Today I'll give a brief overview of the properties of conductors that we can deduce by using Gauss's law and the definition of the electric potential. These are actually some far-reaching properties that give us a lot of physical insight into the way that conductors behave. A perfect conductor, first of all we'll start with this definition, has a very large and essentially infinite number of free charge carriers, which in most normal materials are electrons. And they can carry a current when a potential difference is applied across the conductor. So these kinds of materials, of which metals like copper and aluminum and gold and silver are good approximations, these kinds of materials have several interesting properties, and we'll just go through them one by one and give some very brief justification for them. And the first that you may be familiar with is that the electric field is equal to zero inside a conductor that is in electrostatic equilibrium. And it's important to put that caveat about the equilibrium there. How do we know this? Well, imagine a piece of conductor to which we apply an electric field, perhaps by attaching opposite ends of it to a battery. So there's an electric field E0 applied as shown. What happens in response to that is that the free charge carriers, the electrons, move opposite to the electric field direction because they have negative charge, leaving behind a net positive charge on the other side of the conductor. And what this does is set up an internal field inside the conductor, and we'll call that E1. And its direction opposes the applied field E0, as you can see by the sign of the charge carriers. So these charge carriers will flow until E1 is equal and opposite to E0. And when it does, the charge carriers will then experience a net field of zero inside the conductor, and they will stop moving, which is the very essence of electrostatic equilibrium. So this process by which the charges flow in response to the applied field and then establish electrostatic equilibrium, this happens very quickly. It does take a finite amount of time, but so quickly that we usually don't notice it. Second property that follows directly from Gauss's law is that inside a conductor that's in electrostatic equilibrium, the charge density must be equal to zero. And of course by this we mean the net charge density, when you add up the contributions of all positive and negative charges. How do we know this? Well, in differential form, Gauss's law says del dot E is rho over epsilon 0. And property number 1 tells us that the electric field must be 0, so del dot E is 0, and that means the charge density inside must be 0. So, two very simple properties of conductors in equilibrium. A third one is a rather simple one too, and it says that if the conductor is not neutral, if there's a net positive or negative charge, perhaps because we've deposited excess charge onto the conductor, any net charge that there is must reside on the surface. And of course the reason I know that is because property 2 says that inside the conductor the net charge density must be 0, and therefore if there is any net charge it must be on the surface. The conductor that I've shown here in the diagram is a solid conductor. Of course, the surface, then, there's only an outside surface to it. But one can have conductors with cavities carved out from the inside. And that kind of a conductor can have both internal and external surfaces. And either one of these can have charge on it. But it cannot be in the interior of the conductor. It must be on the surface. Moving along, we can deduce several more. First, we can say that the electric potential is constant everywhere inside or on the surface of a conductor. And constant V means that all of these points are at the same potential. And so these points are referred to as equipotentials or equipotential surfaces. How do I know this? Well, since E is equal to 0 inside a conductor in equilibrium, then for any 2 points A and B that are either inside the conductor or on its surfaces, the difference in electric potential between those points is minus the integral E dot dl from A to B, and that has to be 0 because E is equal to 0 inside. And if that integral gives 0, that means VA and VB are the same. So the 2 points inside or on the surface of the conductor have to be always at the same electric potential. Another property is if we look at the situation just outside a conductor on its surface, we can deduce that E, the electric field, must be everywhere perpendicular to the surface. Now, why is this? Well, here, let me show you the way it looks. This is what we have for an arbitrary shaped conductor. Let's imagine that there is net charge, positive charge, on the surface as shown in the diagram. If the electric field had any component along the direction of the surface, if it was not perpendicular but had some small component along the direction of the surface, then these charges, which would be free inside a conductor, would feel a force along the direction of the surface, and then they would move in response to that. But of course, that would happen very briefly until this condition is established. So one may deposit charge at a single point on the surface of a conductor, but very rapidly that charge will spread out and distribute itself so it reaches electrostatic equilibrium, at which point the electric field lines will always be perpendicular to the surface. Note that that doesn't mean the electric field lines are in the same direction everywhere, because the conductor may have interesting curvature. So it's everywhere, however, perpendicular to the surface at that point. And the final property we can deduce is similar to the one, number 4 on top, but has slightly different reasoning. This pertains to the cavity inside a conductor. So if you have a solid piece of conductor and then inside you've carved out a hole, and if that cavity has no charge inside, we can show that the electric field inside that cavity must be 0. How do we know that? Well, here is a gray-shaped conductor with a cavity inside of it, and since any 2 points A and B that are in the conductor or on any of the surfaces of the conductor, any 2 points are at the same potential, A and B in this case, we can define some arbitrary path between them and calculate the potential difference. And we know it's got to be 0, okay, because these 2 points are in the conductor. What we don't know for certain is the nature of the electric field in the cavity. Okay, we know the electric field in the interior of the conductor is 0, but this cavity is the empty space. So we don't know for sure what E is inside the cavity. However, we do know that A and B are at the same potential, so minus the integral E dot dl from A to B has to be 0. And the only way that this will always be true, no matter what path we choose, is if E is equal to 0 everywhere in that cavity. So we deduce it by virtue of the fact that A and B are at the same potential. All right, so these 6 properties tell us a great deal about the physics of conductors, and let's apply one of those properties right now to solve a problem. Here's an example. A point charge 5q plus 5q sits at the center of a conducting spherical shell. So that shell is a spherical object that has a cavity on the inside. And that shell has an inner radius A and an outer radius B. The shell has a net charge of negative 3q. Find the charge density on the inner and outer surfaces of the conductor. You have a homework problem very similar to this. So here is a sketch. The spherical shell, shown in gray, has an inner radius A, outer radius B, and at the very center has a point charge plus 5q. But the shell, we know, because perhaps we've deposited some charge on it, the shell has a net charge of negative 3q. Well, we know from the properties of conductors that that negative 3q charge has to lie on the surfaces. And so the spherical shell has an inner surface and an outer surface. So we can take that total charge, negative 3q, and say that of that total charge, some of it will be on the inner surface and some of it will be on the outer surface. Together, they add to negative 3q. All right, that's our starting point. The strategy in order for enabling us to solve for q inner and q outer is to choose a Gaussian surface that distinguishes between them. In other words, a Gaussian surface that will enclose one of those charges, but not the other one. And it's pretty obvious to see what will do that, and that is some sort of Gaussian sphere that is large enough to enclose the inner surface, but small enough that it lies within the outer surface. All right, and so we write down Gauss's law for that spherical surface. Integral E dot dA is Q enclosed over epsilon 0. And note that this Gaussian surface lies within the conductor, where we know the electric field is 0. So the left-hand side of the integral is 0. The right-hand side is easy to write down because that spherical surface encloses the point charge at the center, the plus 5Q, plus the charge on the shell that's on the inner surface, the Q inner. So the right-hand side becomes Q inner plus 5Q over epsilon 0, but they have to add to 0. So right away, Q inner is equal to negative 5Q. Bing. That's the first thing we can say right away. And that means that we can calculate the charge density on that surface, because that's going to be charge per unit area. 4 pi a squared is the surface area. So that's the first part, solving for sigma inner. And since we found Q inner and we know the total charge is negative 3Q, Q outer falls out directly as plus 2Q, because negative 5 plus 2 is equal to negative 3. So Q outer is plus 2Q. Sigma outer, note, however, that, I've made a mistake here. All right, I'll tell you what the correction is. The problem is sigma outer should have the charge on the outer surface divided by the surface area of the outer surface. So the denominator there should be b squared rather than a squared. So it should, the final answer should be plus q over 2 pi b squared. So this illustrates the use of Gauss's law and our knowledge of the properties of conductors. Several of those 6 properties have been employed at one point or another in the solution to this problem. Again, you'll have something similar for your homework, and I will look forward to seeing you in class.